Well, welcome everyone to my live weather and climate office hours. Trying to get back on a slightly more regular schedule as my own work travel schedule calms down a bit this month and next month. And at some point, I do want to try to establish sort of a pair of times, since I know some folks are consistently either available or unavailable in particular windows. So maybe try and alternate between weeks. My plan, I think, in the long run is to find two different times on alternating weeks that are regularly scheduled. Probably one weekday morning and another weekday later afternoon. And then also there will be some sessions that end up being off cycle, either in addition to or replacing some of the scheduled sessions when there are episodes of interesting or unusual conditions going on, particularly in California, but perhaps elsewhere too, that warrant more real-time or live discussion. So I think that's the medium-term view. I need to figure out exactly which times would be good, but for now, I'll continue to sort of have these about once a week on a somewhat ad hoc basis, but I do want to sort of nail down a more consistent schedule. That's a goal for moving forward. So with that programming note, I'll dive right into it. I do want to talk about the weather that's happened recently in California, really over the last week or so, and what's coming next over the next week or two to come. I'll talk a little bit about the snowpack in the Sierra, because I know there have been a lot of questions from journalists this week. If I haven't answered your emails this week, it's because there are very many converging deadlines occurring after a period of intensive work-related travel, and unfortunately, the work travel doesn't let you get a lot of the actual work done. Some of you are probably more familiar with that feeling than others. But anyway, I do want to talk about that here in a more consolidated way. Feel free to pull, as always, audio and video, as well as quotes from these sessions. And the other thing I want to talk about, slightly bigger picture, is the ongoing conversations, including a number of high-profile op-ed, opinion, and perspective pieces, even by climate scientists, on how to think about the recent spate of record-breaking, or really in some cases record-shattering, regional, continental, and even global scale heat extremes. We continue to experience extraordinary and record-breaking global, especially global ocean warmth that we've never seen before in the recorded era of temperatures. And so, what that means and what it doesn't mean, and what we know, what we don't know, because there are both some certainties and some uncertainties there, but also a lot of very confused messaging, and I think a lot of that comes down to some challenges with numeracy in the headlines. This has become a pretty major problem, being able to differentiate, for example, between quantities and the rates of change of quantities, and the rate of change of the rate of change of those quantities over time. In other words, the first and the second derivative, or the rate of change and its acceleration. So we'll talk about all of that in the latter portion of the session, and then as usual, I'll take questions live. Just a bit of administrative housekeeping for those of you who are newcomers, since I know that there are a number of folks who are new in the last couple of weeks, so welcome. So recently in California, we've seen a return, as I mentioned in my last session and in the most recent Weather West blog post, which is, by the way, still relevant, talking about the weather that's going to come over the next week or so, a return to active and cooler conditions. Nothing extraordinarily cold, but definitely chillier and showery, and in some cases thunderstormy. And I think a lot of folks sometimes when they think of showers in California think of drizzle or sprinkles or sort of these gray monotonous skies as intermittent light precipitation. But of course that's not always what's meant by shower. Showers can be torrential. Showers can lead to flash flooding and under the right conditions. Now they don't always in California. We do tend to see are a disproportionate share of gentle showers along the west coast because of the typical lack of atmospheric instability. So we tend to get showers that are driven by frontal systems, by orographic precipitation, meaning uplift by mountains. But occasionally we do get more convective precipitation, meaning precipitation from large cumulus clouds and cumulonimbus clouds or thunderstorms amid an atmosphere that is at least somewhat unstable, meaning that if you give a little shove to a parcel of air, it wants to spontaneously continue to rise. So you don't have to have a mountain that forces it upward. You don't have to have a front that forces it upward. In fact, the atmosphere is sufficiently unstable and buoyant that individual air parcels will continue to spontaneously rise and cool and condense into tall cumulus clouds that can produce those intense showers and thunderstorms, even if the only thing acting on them is the ambient instability of the atmosphere itself. And we've seen a lot of those conditions this winter. They've resulted in record-breaking and historic short-duration rainfall extremes in places like Oxnard and Long Beach and parts of Los Angeles and San Diego. So a lot of these events in Southern California, but also localized events near San Francisco and near Sacramento at other points this winter. So we've seen a lot of convective activity this winter. We've seen a lot of thunderstorms. Almost every system, as I mentioned last time, this season has been associated with fairly extensive thunderstorm activity by California standards. At least, always important to add that caveat, because in many parts of the world, the primary mode of precipitation is convection and thunderstorms with much greater frequency than California, which has one of the lowest background frequencies of lightning of any continental region on Earth. It's really tied for some of the lowest regions on the planet outside of the Antarctic. Even much of the Arctic, by the way, or subarctic at least, sees more lightning than coastal California. But anyway, we've seen a fair bit of it this winter. You've seen some severe thunderstorms. You've seen a decent number of tornadoes. I think California's up to 6 or 7 tornadoes so far in 2024, which is notable because it means that California has seen more tornadoes than a number of places in Tornado Alley so far this year. Now, that is not quite a fair comparison because in Tornado Alley, tornado season doesn't really begin until about April and continues through June or July. So we really haven't reached peak season in the part of the country that sees a lot of tornadoes. But still, that's always a fun and interesting statistic that California is ahead of places like Oklahoma, and Nebraska, and Iowa so far this year. Not that uncommon because California, to the extent that it does have a tornado season, does occur earlier. It's often late winter and early spring rather than spring and summer because it tends to be when the cold air at upper levels of the atmosphere coincides with a stronger sun angle and warmer lower altitude temperatures as we sort of climb out from winter. So we still get some winter-like atmospheric circulation patterns and winter-like upper atmospheric temperatures in March and April, but we start to see warmer temperatures at ground level because with those sunny breaks, that strong late March sun, as the sun angle increases, it's no longer so low on the horizon, but you get more direct sunlight. Insolation, not insolation, but insolation, which is insolation, meaning incoming solar radiation. It's actually a compound word, tortured acronym, whatever you want to call it. But as the sun angle increases, as the season goes on, as we get away from the winter solstice, it means that the sun is more easily able to heat the ground rapidly and therefore through conduction and convection, heat the lower atmosphere boundary layer more effectively at this time of year. So when we do get those cold air events aloft and a moist atmosphere coinciding with it, we get that unstable atmosphere, which leads to thunderstorms. So in other words, March and April is peak thunderstorm season, such as it is in coastal California and in the Central Valley of California. And that is very much relevant to the pattern we've seen recently, where there's been conspicuous lightning events in the Bay Area, near Sacramento, in the foothills, and across much of coastal Southern California on quite a few days recently. It doesn't happen like that every year, but if it does happen, this is the peak season for it, for those reasons, and we're certainly seeing it in spades this year. And we're going to see a lot more of it. The forecast for the next 7 to 10 days, at least, continued periods of showery weather with a fair bit of instability and a pretty good likelihood of thunderstorms, including some localized severe thunderstorms at times that could produce coastal waterspouts, a really photogenic one, by the way, Some other West viewers sent in some photos of it near Santa Cruz a couple of days back, or even some mini supercells over the Central Valley, which could lead to, as is often the case, significant accumulations of hail, or even an isolated tornado. This is going to be a pattern that kind of repeats itself every few days for the next week or so at least, so more of this to come. And these systems tend to be, or at least have the potential to be, decent snow producers in the mountains because they are relatively cold aloft. So these are not really warm storms in the same way as we saw earlier in the season. They may not be associated with really coherent cold frontal passages, but they will bring renewed rounds of showers and isolated thunderstorms and even some localized severe thunderstorms, along with some decent Sierra snowfall potential at times. It does look like around Friday and Saturday this coming week, so in about a week from now, I'm discombobulated. Less than a week from now, later this week. Today is Monday, so Friday, Saturday, so 5 or 6 days from now, there will be potentially a stronger system, a larger system that will affect Southern California more than some recent ones have, and could bring some heavier rainfall once again to the transverse ranges in Southern California. So that storm won't really necessarily be a weak one. That will be probably more a moderate to maybe a strong one, probably most likely moderate, but that'll be a more significant storm, focused more on Southern and Central California, and could be associated with a decent atmospheric river plume into Southern California. Still pretty cold air aloft, but maybe some warmer air near the surface in Southern California. So this could be a very effective rain producer for coastal Southern California, once again boosting those seasonal totals as we get toward the very end of March, really emphasizing that back-weighted season that I've been talking about since September or October really is coming to pass. It's been quite wet starting in January and looking like it's going to round out the month in March quite wet in Central and Southern California too. These do look like decent precipitation events for the Sierra Nevada, although nothing huge. It will continue probably to bolster snowpack. It won't massively increase it, but it will probably keep it as a fraction of normal roughly where it is now, maybe 1% or 2% in either direction, which is relatively good news because the snowpack right now is in pretty good shape. In the far north, we're a bit above 100% of average. In the south, we're below 100% of average, but most places are above about 85 to 90% of average for April 1st, and April 1st is historically the peak of snowpack season. So those are pretty good numbers, given that we're now comparing it to essentially what would historically, without warming, be peak season numbers. That's not too bad. Now, there is a bit of a nuanced picture. The numbers are better on the western slope than the eastern slope. The numbers are better in the north than the south, and the numbers are better at high elevations versus low elevations. And a lot of this is a signature of a winter that has featured some storms that haven't made as much eastward progress as we might have hoped, but also of a particularly warm winter. This has been a very warm winter in portions of California. Not the whole winter being super warm, but overall, if we count December through February, or even through March, it has been warmer than average, significantly warmer than average, more often than not, across most of California, and indeed really the whole West. So it's been, on average, in 2/3 of California, I'd say, a warm and wet winter. But in the sort of the Sierra Nevadas, particularly the northern and central part of the range, really the whole range, it's been a little bit drier than average. So it's been a relatively warm and slightly drier than average winter, even though, because of these recent series of wetter, colder storms, snowpack itself, overall, is not so far from average. Even though it's been both warmer and slightly drier than average in the mountains, it's been then warmer and significantly wetter than average across almost all of coastal California. So essentially all of coastal California, from the north coast down to the Mexican border, ended up seeing a wetter than average winter this year. It was significantly wetter than average in portions of coastal central and southern California, less so as you go north. But generally speaking, this has been a pretty good water year. Not as extremely wet as last year, but wetter than average on a statewide basis, and it looks like March is actually going to further bolster that picture. So last winter was, believe it or not, a cooler than average winter overall, which is rare these days in a warming climate, but very wet. This winter was wet again, but much warmer than average, which is more consistent with the kinds of wet winters we expect to see in the future. And of course in the present relative to the past in a warming climate. So warm and wet is a lot more likely than cool and wet in a warming climate. And we're sort of seeing how those winters play out differently this year versus last year, for example. So snowpack is in pretty good shape. At this point, it looks like it will not suddenly melt in the next couple of weeks, so it will remain in relatively good shape. This is not going to be a major drought year in California. It's safe to say, just based on what's already happened. We don't know exactly what's going to happen next. It could be an extremely hot summer, and we could fall back into very dry conditions next winter, theoretically. But my point being, between now and the end of the calendar year, just based on what's already happened, there's not going to be water supply problems. We're not going to see large-scale landscape forest mortality this year from lack of water, for example, in the soil column. This isn't going to be one of those years. Now, the wildfire story may play out differently than last year, and I do expect this year to be more active than last year for multiple reasons. But I'll talk more about that in a later session. But all of that is just to give context for the series of cool and relatively wet storms that are going to move through in the next week or so, with, again, a focus with the bigger storm in about 5 or 6 days from now in Southern California. But it'll also get wet in Northern California and bring some decent snow up to the north too. This also, once again, looks like a significant convective system with a fairly high potential for at least some isolated to scattered thunderstorms, once again throughout much of California, from the Central Valley, especially from the Sacramento area southward, and across coastal Southern California this weekend. So it could be another good cloud watching weekend, and there could be some additional severe thunderstorms locally. It's really too hard to say at this point exactly where, but this is the kind of pattern that stands out because there will be both sufficient atmospheric instability and also some decent structure of the jet stream overhead to induce some upward vertical motion in the atmosphere, so to accentuate, to give the atmosphere that initial kick that it needs to get those rising air parcels that can turn into thunderstorms. So active pattern continues. They'll probably be with the system, if it holds together as currently anticipated for Southern California, particularly transverse ranges, some flood risk. It'll be not as extreme as the systems earlier this year because antecedent conditions aren't as extremely wet, and this system itself doesn't look extremely intense. But there could be some localized heavy rainfall, including some heavier downpours where there are thunderstorms. And given that it has been a relatively wet year, the watersheds will probably respond pretty quickly if that happens. So in the transverse ranges, I wouldn't be too surprised to see some flash flood watches go up if this system continues on its projected path by about Friday or Saturday. I don't see a particularly severe or extreme flood threat, but there will probably be, once again, a period of some potential for some urban flooding or some moderate flood risk in the transverse ranges if those thunderstorm downpours materialize, or if that moderate strength atmospheric river becomes a bit stronger or stalls out again. We've certainly seen that happen this year multiple times. So again, right now, not looking like any kind of extreme event, but I would say most likely a moderate storm in Southern California, maybe a strong one if the upper end of the ensemble comes to pass, along with some pretty decent thunderstorm activity again, and some accumulating Sierra snowfall. Probably not a huge Sierra snowstorm compared to the ones we've seen earlier this year, but it will keep the snowpack up. So I think that about covers California. This is, the El Nino is rapidly fading, and so the atmospheric signature of El Nino is really starting to go away pretty quickly. So the active weather that we're likely to see in the coming weeks is probably less and less connected to El Nino, probably more directly related to an active phase of the Madden-Julian oscillation, so that subseasonal oscillation in the atmospheric wave pattern that emanates from the tropics that can lead to jet stream extensions and active weather over California. When that happens in late March and April, this is exactly the kind of pattern that we tend to see. Cool, moist systems that are relatively unstable given the high sun angle, but the cool air aloft. Good recipe for additional precipitation without any really destructive storms, although it does raise the potential for things like hailstorms that can cause problems for agricultural areas in the Central Valley, given that it's the spring and plants are starting to grow and to blossom in some cases. And also for urban freeway driving, it's always a problem when you get those small hailstorms. Hailstorms of small hailstones, I should say. Sometimes the hailstorms are quite substantial and can result in accumulating hail, as some of the imagery from the LA Basin demonstrated over the past couple of days. By the way, it's much more common for hailstorms to occur when the surface temperatures are well above freezing than it is when temperatures are cold. So because it hailed does not mean that temperatures are super cold at ground level. In fact, again, some of the most famous hailstorms in the U.S. have occurred in places where it's quite hot and humid in the spring and summer months, in places like the Great Plains, where sometimes you'll get a major hailstorm on a 90-degree day, or in Texas or the Gulf Coast or in Florida. Again, big hail-producing regions. These come from thunderstorms, and thunderstorms are more likely when you can get warm, moist air in an unstable atmosphere near the surface. So the hailstones, I should say, form, remember, at very high altitudes where it's always very cold. You're thinking up at the altitude where jet aircraft fly, where even at peak summer, the air temperature might be minus 20, minus 30 degrees Celsius. So very cold temperatures where these storms form. Because of the nature of the hard ice balls that they don't melt all the way as they fall through well above freezing air column on the way to the surface. And so that's how you can see golf ball sized hail on a 90-degree day in Oklahoma during severe storm season, because it's clearly not below freezing at the surface, but it's always below freezing if you go high enough up in the atmosphere where those hailstones form. That's a bit of a tongue twister. All right, and there's one more piece of the monologue session that I wanted to get to, and that has to do, as I mentioned, with the global climate situation at present and how extremely warm it has been, both in the atmosphere, but particularly notably in the global oceans. And, there's been some interesting internal conversations amongst climate scientists, even, in terms of exactly how to understand what's going on. And there is, I will say, some disagreement, at least in terms of how significantly to weight the really extraordinary warmth that we saw during most of the 2023 calendar year, and so far continuing well into late March of this year. So up to the present, conditions are still record warm in many ways, in terms of the global oceans especially. There's a couple of different questions here, and I wanted to break them down. And there have been a lot of media headlines suggesting recently that scientists can't explain why it's so warm right now. And I think those headlines are fundamentally misleading and really factually incorrect, as it turns out, because the main reason why conditions are so warm right now is global warming. Full stop. So if the question is, why are temperatures right now, meaning in 2023, 2024, or really the past 5 or 10 years, so we can even generalize more broadly, why are they so much warmer than temperatures that we saw in the 20th century, or really that we've measured at any point in recorded human history? The answer is unambiguously the accumulation of heat-trapping gases in the atmosphere, because that has caused the planet to warm about 1.3 to 1.4 degrees centigrade up to this point. Now, we've been seeing these headlines where we've been getting individual weeks and months where Earth's temperature is as much as 1.5 or 1.6 degrees centigrade above the global mean average. So global warming to date doesn't quite get us that far. It doesn't get us to 1.5 or 1.6. But if it gets us to 1.3 or 1.4 out of 1.5 or 1.6, it's very clearly by far the dominant factor as to why we are where we are today. And so then the question is, okay, but what about this extra 0.1 or 0.2 degrees centigrade? It doesn't sound like a lot, but it actually is quite significant, because we're breaking global temperature records by margins of 0.1 or 0.2 degrees centigrade in recent months, which is a big deal. That's a large margin when we're talking about some globally aggregated quantity. And there the answer becomes a little bit more murky. Part of it is undoubtedly because we emerged from a prolonged La Nina event, which temporarily suppresses the human-caused warming trend last year. So we had a 3-year triple dip La Nina event. Remember that? And that essentially meant the global temperatures were probably 0.1 degrees, maybe up to 0.2 degrees cooler than they would have been otherwise, due to the long-term warming trend. Because La Nina tends to sequester some of this extra energy in the global oceans. It doesn't stay there forever, and it doesn't actually result in a global cooling trend, but you can, during the La Nina event, see temperatures that are cooler than you would otherwise. But then we rapidly transitioned from that La Nina period to what has, by many metrics, been a very significant El Nino event. So it was a strong to very strong event. Different metrics give you different answers as to exactly how strong it was, but it was almost certainly in the top 10 events we've seen historically, globally, and maybe in the top 5 El Nino strength events, depending on the metric. Point being, it was a significant El Nino event on the heels of a historically persistent La Nina event. So that's a major sharp transition from a period where the Earth's natural climate variability, so the variability not caused by human activities, temporarily suppressed the long-term warming trend, to a period where Earth's natural climate variability, again, El Nino, which results in a sort of unearthing of all of that subducted heat that was in the oceans during La Nina, that could result in a pretty significant jump from year to year. And that's what we saw. So we saw a huge increase in temperature from 2022 to 2023, 2024. So that was a really big jump. And part of that comes from the fact that we went from La Nina to El Nino. So we went rapidly from a period where the Earth was artificially suppressing the warming trend to a period where the Earth, through its natural climate variations, was artificially accelerating the warming trend. So then that might explain another 0.1 or 0.2 degrees centigrade of the increase we saw this year. So between those two things, we can clearly see that the long-term warming trend caused by the accumulation of greenhouse gases in the atmosphere due to human activities over the past century or so is the number one cause. And the number two cause, probably, at least in terms of why 2023, 2024 have been so ridiculously warm, is that when you add a strong El Nino event as an exclamation point on top of that long-term human-caused warming trend, that inexorable upward trend that has persisted even in the cool years, it's just that energy has been subducted in the oceans and hidden from us. Well, a lot of it got unearthed during this El Nino event, and we're seeing some of that latent warming manifest now. So the answer to why was 2023, why is it so warm right now relative to a historical or pre-industrial baseline? The number one answer is global warming. The number two answer is the transition from La Nina, which artificially suppressed the warming, to El Nino, which artificially enhanced it. But then that still leaves some additional margin. There's still some additional warming that occurred between 2023 and 2024, where we are now, that can't fully be explained, according to our best understanding of the system, entirely by that transition from El Nino to La Nina. From La Nina to El Nino. But I do want to make clear that there are two different questions here. One question is, why was there such a big jump in global average temperature and in global ocean temperatures in particular, especially in specific ocean basins like the North Atlantic and the North Pacific, between 2022 and 2024? That's a question that we don't necessarily have a complete answer to at this point, and that is the subject of some significant discussion by climate scientists and others right now. But then there's the other question of why was 2023, 2024 so ridiculously warm compared to 100 years ago? Why was it the warmest year on record by such a significant margin? And that answer, again, is essentially settled. It's mostly global warming plus the transition from La Nina to El Nino. And I really want to make clear that these are two separate questions, and unfortunately I've been seeing a lot of headlines that are conflating them. Because the answer to one of the questions is really clear. It's mostly global warming. But the answer to the other question is different. because global warming didn't suddenly massively accelerate between 2020 and 2024. So that can't be the reason why we suddenly had this huge increase in global average temperature and the warmth of the oceans between 2022 and 2024. So it's important to distinguish between those two questions because the answers are actually completely different, and our level of certainty regarding the answer is also very high, essentially unanimous for one, and genuinely uncertain for the other. As I mentioned, a big part of the reason why we saw the big jump in temperature between 2022 and present is the transition from La Nina to El Nino, but it does not appear to be a complete answer. And so essentially we saw a larger increase by, especially in certain regions, than we would have expected. One way to look at this is that this El Nino has not behaved in the same way as many historical El Nino events have in terms of the spatial pattern of the warming and the atmospheric teleconnections. We did, in California, ironically end up getting a pretty canonical El Nino winter from a precipitation perspective, in the sense that it was actually pretty wet in coastal central and southern California, and not necessarily quite as wet in parts of northern California. That is pretty much the prototypical strong El Nino response. But it's been different in other regions, and part of this is just because it's so much warmer than it used to be that we can kind of throw a lot of those historical El Nino temperature teleconnections out the window, because now the global warming trend is larger in many regions, exerting a larger influence than the variability between El Nino and La Nina in terms of temperatures. So essentially it's just so much warmer all the time now that it's overwhelming the variation between El Nino and La Nina. It's still modulating the warming trend, but the dominant influence is just the long-term warming. So this winter was, in some cases, in fact, in many places in the American West, in the top 10 warmest winters on record, and in a few spots, it was actually the warmest winter on record, and that includes some parts of the San Joaquin Valley in California. This was, in fact, the warmest winter on record there. And El Nino did not necessarily mean very warm temperatures historically during winter in central and southern California, because it usually resulted in so much rain. We still got the rain this winter, but we ended up a lot warmer than average in many places. And that's a striking illustration of just how much the warming effect has altered the teleconnections with El Nino and ENSO generally. But on a global context, this El Nino has behaved strangely. There's been record-breaking global warmth, especially in ocean regions and some land regions that you would not necessarily expect during an El Nino event, because a lot of that warming during El Nino typically occurs in the tropics and subtropics, but we saw record warmth well outside of those regions this year. So this is a bit of a weird El Nino, and there's some evidence that climate change may be changing the relationship between El Nino and large-scale climate variables. This is an active area of research right now. We don't have complete answers, but it's something that is actively under consideration. And then there's the wild card question, like, is there something else going on in addition to that? You know, it may be that this was a quote-unquote weird El Nino, and that explains part of it. Part of why the jump was so larger than we might have expected for an El Nino of this magnitude, and also why the spatial pattern was a bit different than we might expect, why some regions outside the tropics were just so darn warm in 2023, 2024. That remains unaddressed, and that is actually the question that a lot of physical scientists and climate scientists are addressing. And when you see some of these opinion pieces and perspective pieces and headlines, that's the piece of this that a lot of these scientists are focused on right now. So it's not that scientists can't explain why overall 2023, 2024 was so extremely warm. It's that we're scrambling to explain the margin. That last 0.1 or 0.2 degrees Celsius is maybe more than we would have expected, as well as the spatial pattern being different. So it's not that climate scientists are completely in the dark about what's going on, as this has been portrayed, and as this has been interpreted, and I think nervously interpreted by many folks. It's not to say that we have a complete understanding of everything that's going on right now, but it is to say that it's not like this is necessarily evidence of things careening out of control or warming occurring much faster than expected. In fact, there's some very compelling plots that you can make putting this year's record-shattering temperatures in the context of climate model large ensemble predictions for what conditions might have looked like in 2023, 2024, and we're well within that distribution of where climate models said we would be right now. So the interpretation that we've suddenly jumped and have warmed much faster than climate models said we would at this point is just factually inaccurate. We are still well within the range of where, within the broader range, and we're not really even that far from the median if you smooth it over a couple of years of where climate models said we would be in terms of global average warming as of 2023 or 2024. Now, it is true that we're in the upper half of that distribution, so we're certainly not on the low end, which I think tells us something interesting, but we're also not at the very top of that distribution, and we're certainly not beyond it. I don't think that should be particularly reassuring because it means that warming is continuing to progress as expected. And by the way, warming has long been anticipated to start accelerating right around this point. So a lot of these folks who have further pointed out that the warming may be starting to accelerate, that probably is true. It's also exactly in line with predictions from climate models that suggested around circa 2020 to 2030 that the rate of global warming would start to accelerate on our current emissions trajectory. That is for two reasons. One, the primary reason, is that this is right around when we expected that our global aerosol pollution emissions would start to rapidly decrease. The aerosol pollution was a kind of pollution, the soot essentially in the atmosphere, that was artificially suppressing the warming trend from greenhouse gases. So there are two different types of atmospheric air pollutions that have really affected global climate on human timescales. One is greenhouse gases. We're all familiar with the heat trapping influence of that. That's the cause of global warming. But there's also aerosols, this soot that we put up into the atmosphere that reflects sunlight before it makes it to Earth, which exerts a net cooling effect. And due to air pollution regulations and cleaning up our factories and our tailpipe emissions, global aerosol emissions have started to decrease. What that means, though, is that some of the warming that the greenhouse gases were causing in the 20th century were offset by cooling from those aerosols. As we start to get rid of some of those aerosols, some of the warming influence that was already being exerted by the greenhouse gases is starting to become unearthed. This is what James Hansen has long called the Faustian bargain, in the sense that we are trading, we're getting rid of one kind of very harmful air pollution, which is good, but in the process, we are probably going to cause an acceleration in the rate of warming. Not because the warming is faster than expected, not because the increment of greenhouse gas concentration is necessarily increasing faster than expected, but because there's this other factor that was previously causing suppression of that warming that's going away. And so we're actually experiencing more of the warming that the greenhouse gases were producing all along than we have been for most of the 20th century. And observations indicate that indeed we are starting to see decreases in aerosol emissions that probably are significant enough to be causing some of this unearthing effect to occur right now. So this notion that the warming is accelerating a little bit, it probably is. And it's mainly for that reason, because of the decrease in aerosol emissions. Now, there's been a lot of focus on ship-specific aerosol emissions as a result of a major policy change in 2020, so sort of a discontinuity in global ship aerosol emissions. Right now, there's not much evidence that this exerts a large influence on global climate, although, again, to the extent that it exerts one, it is a warming effect, probably on the order of a few hundredths of a centigrade of warming so far. But, it is additional warming on top of warming on top of warming. So it certainly isn't helping things. But the bigger picture about aerosols from all sources, so if we're not just thinking about ships, but at ships plus factories plus tailpipes plus everything else, that is exerting a meaningful effect in terms of global warming and is probably the main reason why the warming is perhaps accelerating a little bit right now and probably will continue to do so for a couple of decades as those aerosol emissions continue to decrease against a backdrop of greenhouse gas accumulation that is continuing to accumulate. So we probably will see an increased rate of warming over the next 10 or 20 years. Now, what happens after that is greatly dependent on our greenhouse gas emissions trajectory. So at some point, the influence of the unearthing effect from the decreasing aerosols will saturate. We won't really get any more additional unearthed warming from it once we get our aerosols emissions pretty close to zero, or at least negligibly low. And honestly, it is a difficult trade-off, because on the one hand it results in a faster rate of warming, but it really does have huge benefits, because global aerosol pollution killed millions of people every year in terms of the public health burden. So it genuinely is a trade-off that is, there are costs and benefits to that one. The cost being the fact that it may increase the rate of global warming over the next couple of decades. But after that, as that aerosol effect stabilizes, then the question really comes back down to solely greenhouse gases. What do we continue to emit? And are there any significant Earth system feedbacks that start emitting greenhouse gases beyond our control as the warming continues? We're talking about permafrost thawing, biogenic emissions from rainforest dieback or tropical wetland, peat fires, things like that. That's a question for another day, but the main point is that these headlines that the warming is accelerating, that may well be true, but it is exactly what climate models suggest should be happening right now, and what climate predictions have long suggested might happen right around now. So again, it's not good news, but it's not bad news in the sense that things appear to be completely out of control, and for reasons we don't fundamentally understand. It really suggests that, unfortunately, these long-term predictions were once again quite accurate when it came to both the amount of warming so far and this inflection point in the rate of change. Now, all of that said, there are some concerning trends in things like global methane emissions and concentrations and sort of trace gases. So carbon dioxide is not the only greenhouse gas. It's the one we talk about the most often, but there are others that are far more powerful greenhouse gases. Nitrous oxide and the different, there's a variety of trace gases out there that have much lower concentrations than CO2, but on a per molecule basis exert a dramatically larger warming effect. Now, methane doesn't stick around as long in the atmosphere as CO2. It lasts a decade or two, compared to a century or more for for carbon dioxide. But the point is, those trace gases have actually been increasing a lot faster than we expected. So if we're looking for things that are occurring faster than predicted, the global increase in methane and nitrous oxide concentrations, that is actually happening significantly faster than expected. We don't fully understand why yet. And that is a bit of a concern, because it could further amplify the rate of warming acceleration. And it could mean that the rate of warming in the future might decouple a little bit from the rate of human CO2 emissions, maybe a bit more than we would have expected. Right now, we don't think this is a huge effect. But again, it is an additional warming effect. So it doesn't help the situation, but it also doesn't look like it's an enormous effect at this point. But that is a point of contention, and we don't know exactly why the methane emissions are increasing as fast as they are, faster than predicted. And if that faster than predicted rate of increase of methane continues to persist in the future, that may become a growing problem. It kind of depends why it's happening. Is it that essentially the resource extraction and oil hydraulic fracturing wells around the world, or have these phantom or ghost emissions that are a lot higher than reported? I mean, that would be good and bad news, because it would be bad news because we don't want to see that, but at least the good news would be we know where it's coming from and there are potential ways to mitigate it. Is it because we're seeing faster than expected emissions from tropical wetlands or from tropical forest dieback or from permafrost thawing? That would be worse news in a lot of ways, because it means that that's something we have less direct control over, and that's only going to get worse as the warming continues. So these Earth system feedbacks are a big part of the story, and we don't really have a complete picture on that. And that could end up being one plausible path toward greater than expected warming on any particular carbon emissions trajectory, because we can at least have the potential to control direct human emissions, but we don't have full control over these biogenic greenhouse gas emissions, especially of things like methane. If positive feedbacks or self-reinforcing vicious cycle type processes start to unfold faster than expected. And this is one of the major uncertainties in climate science, is the coupled Earth system feedbacks that might result, that genuinely could result in more warming than expected. There's no real evidence that's a big part of what we're seeing right now, because essentially we can explain the magnitude of what's happening right now for the most part with all of these other things that I was just talking about. But moving forward, that is a concern. And it could turn out to be that they were playing a slightly larger role than we anticipated in this current period right now. A test of this will be if in the latter half of 2024 and into 2025, does this extraordinary warming, transient warming become not so transient? Do we maintain this global mean temperature above or near 1.5, 1.6 degrees centigrade into next year? And that may raise some different questions, because we should see some temporary plateauing or cool down of Earth's average temperature as we head towards what could be a significant La Nina event next year. Because again, La Nina would exert a temporary artificial cooling trend from that natural variability, superimposed on top of the long-term human-caused warming trend. If that doesn't happen later this year into next year, then I think we may be having a somewhat different conversation. So my point is, this is all really complicated. A lot of the headlines I've seen recently are factually wrong, even though the content, as usual, of many of these pieces and articles is great and accurate in most cases. So read beyond the headline, and if you're a headline writer, think really carefully about the difference between faster than predicted and acceleration. It's quite possible that a prediction might have been that the rate of change would accelerate, and that's in fact exactly what the case is here. And also differentiating between the two very different questions of why is it so warm right now overall, and the answer is mainly global warming plus the transition from La Nina to El Nino, and the separate question of why was the margin by which 2022 to 2024 broke records so large. That is not primarily a global warming answer, and the transition from La Nina to El Nino is only part of it. So the rest of that question is more interesting. And the question about what happens next. Are biogenic carbon emissions going to be greater than anticipated? That could be a problem. And I don't think we have, honestly, a great handle on that. We know it will contribute some amount of additional warming beyond directly human-emitted CO2, but we don't have a good handle on how large the effect will be. Right now, we think it's modest, at least to date, and it will remain relatively modest on a trajectory of sort of emission stabilization and then decrease, which is what we appear to be on. But there are some large uncertainty bars on that, and the upper end of them would be pretty problematic. And right now, there's not a lot of evidence we're going to end up on the low end of that particular uncertainty, and there's some evidence we're ending up in the upper half of that Earth system feedback biogenic carbon emissions part of the distribution. So it's something that, honestly, it's one of the big uncertainties. It's one of the big unknowns about what the next 50 years is going to look like. That's a big part of it. So still, the overriding uncertainty is what will we humans do politically and socioeconomically to curb our emissions and bring our direct human emissions down close to zero. But then there is this question, we think it's a secondary question right now, of what the Earth system will do in response to the warming that we're going to see still over the next few decades. And there are still some big uncertainties there. So I know that's a lot. There's probably a lot of questions coming in. I want to take a look at the questions that have come in. I know I had a pretty long monologue today, so I'm going to take a sip of water and then take a look, start tackling the questions. Okay, not too many today. Question from Mike about what the current status of the coast-adjacent upwelling current off the coast of Southern California is right now. Is it ramping up yet? Well, just, I can take a quick look myself in the background as I talk at the current ocean surface temperature anomalies near California, and actually the water off of California remains unusually warm by 2 to locally 3 or 4 degrees Fahrenheit, which is significant for an ocean temperature anomaly. That is, by the way, I still think part of the reason why we've seen so much thunderstorm activity this season in California. There's just this extra juice and warmth of the lower elevations, lower altitudes of the atmosphere, particularly in the boundary layer, contributed by that warm ocean. But what it also suggests is that the upwelling is certainly not stronger than usual and probably a little bit weaker than usual right now. That's the main mechanism by which nearshore ocean temperatures in California get warmer than average. It's not necessarily because you get warm water moving in from elsewhere. It's just that you kind of kill off some of the cold water cycling upward from beneath with that upwelling. So I think right now, overall, on a multi-week basis, the upwelling has been weaker than usual. We'll see how much longer that lasts. A question from David. Can you confidently say whether long-term warming will bring a decrease or increase in precipitation in California? Is there any chance that a warmer California might be wetter? So this is sort of a signature theme, if you ever heard any of my public talks, or really a lot of these conversations on YouTube, which is that no, we really don't know if the average annual precipitation in most of California will increase or decrease. There's a slight tilt in the odds towards increase in Northern California and a slight tilt in the odds towards decrease in Southern California. But my overwhelming emphasis is that it doesn't really matter because the change in the average precipitation is likely to be small and of uncertain sign, but the changes in everything else related to California's hydroclimate are likely to be profound and dramatic, and we understand them much better. In short, we expect to see more variability, more extreme swings between very wet conditions and very dry conditions. We expect to see larger increases in extremely wet winters and extremely wet individual storms, possibly at the expense of more weak to moderate storms. So we expect to see more intense atmospheric river storms, but potentially fewer of the rest of the storms. And this will vary from year to year. We'll get some exceptionally wet years, and perhaps a slight increase in the number of very low precipitation years as well. But from the dry side perspective, what's really going to be the dominating factor is this massive increase in the evaporative demand by the atmosphere, the thirstiness, if you will, by a warmer and drier atmosphere. As that vapor pressure deficit, as the size of that atmospheric sponge expands, meaning that we will see wetter years in the future. Many years in the 21st century in California will be much wetter and much warmer than their 20th century counterparts. But we will also see a number of years that are somewhat drier and warmer of course being the key theme here, but that are exceptionally dry from a soil moisture and a vegetation and a water supply perspective because of the profound increase in the propensity of a warming atmosphere to extract more moisture out of the land surface. So we will see more severe droughts in a warming climate in California, almost undoubtedly. We already are. But the main mechanism there is not because of a large decrease in the mean precipitation. It's because of this increase in the evaporative demand by the atmosphere, this increasingly powerful atmospheric sponge that draws water more and more rapidly, more and more efficiently out of the landscape when it's not raining, and also an increase in the number of overall dry days and a truncation of the length of the rainy season. So shorter, sharper winters. We'll still get plenty wet winters much of the time, and some of them will probably be wetter than anything that we've seen historically. But we'll also get the very dry winters, and they will feel even drier than they used to because the precipitation may be just as low as it was historically, but the evaporative demand is that much higher. So what little water we'll have in those winters will be even more scarce, essentially, because the atmosphere is going to suck even more of it out of the soil. All of that's happening in the context of uncertain and probably modest changes in overall average annual precipitation. So we'll see more seasonal whiplash, drier autumns and springs but wetter winters, hotter summers and therefore more intense evaporative demand. And yet all of this occurs in the context of increased flood risk and increased drought risk, absent a large change in the average annual precipitation. A very complex picture, And it just illustrates why I think California, and this is true even of some state planning that's happened in the last decade, and some state agencies that really focus heavily on changes in mean precipitation, we do that at our peril because it's going to completely mischaracterize the changes that are most likely to happen in a warming climate. So warmer, certainly, of course, but wetter and also drier, depending on the year and the season that you happen to be in. So we'll see wetter wets and drier dries, and I don't know what's going to happen with average precipitation. It really could go either way, and there might be a split somewhere where the northern third gets slightly wetter and the southern third gets slightly drier. But I don't think that those mean trends are really going to be what's really the predominant influence on the hydroclimate impacts that we see in terms of drought, flood, and wildfire risk. It'll be everything but the mean that matters. A question from Michael: would this wetter, more convective pattern we've been having here in California now in March happen even in an average year without El Nino? I'm assuming that's in the context of a warmer climate. That's a very interesting question. I've been asking the same question myself. I don't have a clear answer, but my hypothesis is yes. Although it won't happen every year. You still need that cold air aloft, which means you need that Gulf of Alaska storm influence. So we'll see some warm and wet winters probably that are not very convective because the whole column is just kind of warm. But then we'll see some years like this one where the upper altitudes are still cold, but the lower altitudes are quite warm and moist, and where we potentially see a lot of thunderstorm activity. I've talked about this in recent sessions, that my personal hypothesis is that California may see more thunderstorm activity in a warming climate, and perhaps an increase in the still rare, but maybe slightly less rare, instances of severe convective weather or severe thunderstorms in certain parts of the state. Again, there is zero academic research on this to date, so I don't really have any papers or research I can point to except for sort of our own informal thinking and a few data points that we've got from some model simulations so far. I don't know of anybody who's even planning to do this research. This is the problem. There are so many scientific questions to ask. There are so few resources to ask them. I can't run all the studies. So, but if somebody's interested, let me know, and we could cook something up. Noah asks, has there been any new research into the anecdotal rise in extreme precipitation events globally? Well, it certainly isn't anecdotal. There is abundant evidence formally and objectively that, globally speaking, extreme precipitation events have already increased significantly and continue to do so. This is true for the U.S. as a whole, stronger in some regions than others. Some studies that ended 5 or 10 years ago didn't detect the signal yet in western U.S. and California. I am pretty sure that if we included data through 2023, 2024, that would be different. That might be a study that we are able to tackle in the next year. I've been talking with some partners at the National Weather Service and at UC Merced. Maybe that'll move forward. But again, it's a question of resources and time, and there are only so many hours in the day, and someone's got to, each paper takes, months of person effort. And so you got to find a way to fund that, months of person effort salaries. You got to find thousands of dollars to publish your paper because, even the open access society journals still charge thousands of dollars for scientific authors to publish. There's a misconception that scientists get paid to publish, but in fact it's the opposite. They have to pay. Some journals now for open access charge as much as $10,000 to $13,000 per paper. So if you've got excellent funding, you might be able to pull that out of your research grant. But that's a steep hill, considering that you have to find funding to support yourself to do the research, then you got to find funding to support yourself to publish the paper. That's supposed to be the role of. Now there's a whole conversation about how this is becoming ridiculous and how it's insane that scientists have to pay thousands of dollars to publish papers, which is something I agree with. But in the current system, this is often the way it works. And there are open access journals. Some of those still charge thousands of dollars, by the way. Some of them are not as expensive. But then we have the issue with some of these open access situations leading to sort of this paper mill situation and the explosion of AI fake papers out there. That's a whole nother conversation. There's a whole field of study on the ethics of scientific publishing, the importance of society journals versus the quote-unquote prestige journals. And I think that that's a strong argument, although I also think some folks overlook the value of having full-time paid editors, to the extent that the papers, honestly, that have better figures and are more heavily edited so that they are more accessible to broader audiences, I do think have greater potential for societal impact and for uptake in planning. So there are trade-offs there. Maybe that's an interesting conversation for another day. It's fairly tangential, but anyway, that's what you get. You get my stream of consciousness, unedited thoughts flowing to you live via YouTube in these sessions. So I suspect that's why many of you are here. Plenty of opportunities to see me in more formal settings elsewhere. There's a question about geoengineering. We're already past the hour. That's a big question, so I'll talk about that in some other session. A question from Jeff: what is ultimately driving the noticeable and significant Thule ground fog in California's San Joaquin Valley that doesn't ever get mentioned, but it has changed significantly in 30 years? There is evidence that it has significantly decreased, quite dramatically. In fact, Thule fog has in some years been largely absent. Part of that is because we've seen a lot of warm and dry years recently, which is not conducive to the formation of fog in the Central Valley and the San Joaquin in particular. There's some evidence that part of it, again, has to do with the fact that air pollution has actually decreased, and so the cloud nucleation for Thule fog was partly because the air pollution was so bad for much of the 20th century that it artificially increased the frequency of Thule fog. I'm not convinced that's the only thing that's happening, although I'm willing to believe that it is a significant factor. I do think that there probably is the case that in a warming climate, we get a warmer, drier boundary layer where fog should form more often than we used to. So that should probably inhibit Thule fog formation. We've seen more of it in the past couple of winters, although not a lot this year, honestly. More last year. I think there probably is a climate change signal here too, in addition to an anthropogenic aerosol emission perspective. There was a paper that came out that found that the aerosol pollution decrease was the main reason, but it was a study that wasn't really designed in a way that could possibly take climate change into consideration meaningfully, so I'm a little bit skeptical that that's the only thing that's going on, although again, it probably is part of it. We know that local air pollution can profoundly affect cloud nucleation and fog creation, so this would be precisely where you'd expect that to be maximized. So it's probably, honestly, my best guess, it's a combination of decreases, ironically, in air pollution and of climate change. So two different anthropogenic factors, and I honestly don't know which of them is more important in this particular context. There'll probably be more studies on that moving forward, but I suspect it's both. The question that what's causing La Nina now that the oceans are so warm, it doesn't make sense. Well, La Nina doesn't really care about how warm the ocean is globally. La Nina is a process, it's essentially, again, you can kind of think of ENSO cycle, the transition from El Nino to La Nina and back again, as a bit of a spring oscillator. Here, I've got a rubber band in front of me right now. So if you hold it in front of you, you can think of essentially of the El Nino and La Nina cycle being this oscillation between you pull the band, you pull the spring, and then you let it go. And if it's a spring, it's kind of going to naturally oscillate back and forth. This is something that is a natural oscillatory process. It is a true cycle, and the way a lot of folks say all these 3 and 4 letter acronyms are cycles, and they're not really physically well understood cycles in the way that El Nino, La Nina, the ENSO cycle is. ENSO really is this semi-periodic cycle, 2 to 7 year period, and it does spring back and forth because El Nino is a collapse of the typical state of things. So normally you have tropical winds that blow from east to west that maintain the upwelling in the eastern tropical Pacific and maintain the downwelling in the western tropical Pacific. So you have this gradient of very warm water in the west and very cool water in the east. That's the normal state of things. El Nino represents a disruption of this pattern where you lose the tropical easterlies that either are weaker than usual or go away completely. You actually get tropical westerlies that essentially cause this warm water to slosh eastward across the tropics and kill off that cool water upwelling in the eastern tropical Pacific. La Nina, on the other hand, is actually a reinforcement of the mean state. So it's not a collapse of these tropical easterlies, but it's a strengthening of these tropical easterlies. So an enhancement of the way things normally are, absent El Nino or La Nina. So you get stronger easterly winds, you get more upwelling. So that cold water off the coast of Peru in the eastern tropical Pacific, it's not cold water that's flowing in at the surface from somewhere else. It's cold water that's coming vertically upward from the depths of the ocean as the oceanic upwelling strengthens due to the shift in tropical wind patterns. So this is a case where in 2024, we're going to see an extraordinary La Nina event with record-breaking ocean warmth, it looks like, in the subtropics and extratropics and in the Arctic, but really cool water along the equator in relative terms in the tropical Pacific. And I'll actually show you what that might look like very quickly. Well, I'll show next time. I don't have it up on the screen right now. But there'll be a pool of unusually cool water, a small one, potentially very cool water, right along the equator in the eastern tropical Pacific, and the rest of the global oceans appear fiery red. So a blue blob in the eastern tropical Pacific near Peru, and a very red ocean and temperature anomaly map just about everywhere else. That's how that can happen, and that's probably going to result in a La Nina unlike what we've seen in historic times this year, which is one of the reasons why I'm wondering, and a lot of climate scientists are closely watching what happens with global average temperatures this year and into next year. The assumption is that they'll level off or probably drop a little bit relative to where they are right now, at least, remaining, of course, very elevated due to global warming, but at least not as high as they have been recently. But we'll be watching closely because the ocean temperature patterns we see right now are not typical for a La Nina event from the 20th century. And honestly, we're not 100% sure what that's going to mean for global temperatures. And if they don't come down in 2024 into 2025, that's going to require some further explanation. And that is precisely the question that a lot of climate scientists are wondering aloud about right now that have been misinterpreted in a lot of circles. That's the kind of question where we're saying, this is interesting. It's not, I wouldn't say it's concerning yet. If it still looks like this in 12 months, though, that it might be more so. That's kind of where things are right now. Question from Mark. Given the new climate change context that ENSO is in which it's operating, how useful are historical records of La Nina and El Nino in predicting expectations of forecasted future El Ninos and La Ninas? This is an important scientific question. I actually know my colleagues are doing this research. I've seen some initial results from some of my colleagues here at NCAR. There'll probably be a study out in the next 6 to 12 months about this. And the answer is it probably is changing. But exactly how, we're not quite sure, because we actually don't know still whether the climate change is going to cause a trend towards a more El Nino-like state, as climate models have suggested previously, or a more La Nina-like state, as the world has actually trended toward. Are the climate models wrong, or are we experiencing a particularly weird iteration of random natural variability? We don't know. We genuinely don't know. That is perhaps one of the most consequential uncertainties right now in terms of the next couple of decades, and how they're going to go in terms of climate science. This is why it's kind of funny when folks get upset when there's this saying that the science is settled about climate change, and all that really means is that we know that global warming is real. We can observe it; it's in front of our eyes every day. We know that the cause is primarily overwhelmingly, really, the human-caused increase in the accumulation in the atmosphere of heat-trapping greenhouse gases, and that it's going to continue for as long as that happens. That's where all of the settled science is. But when it comes down to the details, there's actually a lot we still don't fully understand. In fact, there's some indication that there are some big things that we don't understand that have become more apparent in the last few years than they were, say, even 5 or 10 years ago. So the big picture isn't going to change, but there are some very important things that at a global scale might be considered details, but from a practical perspective are not details at all. They're hugely consequential, and they will greatly affect the manifestation of climate change in particular regions. The ENSO changes that we may or may not experience is definitely one of those things. All right, well, thanks for the kind words. I'm glad that the video and audio quality has been good. I did do a speed test this morning, and it was, speaking of things that are unprecedented, my upload speed was unprecedented today even for a hardwired connection. So maybe the squirrels have relented, or maybe the long-term cable replacements have proceeded faster. So in any case, I'll knock on wood that continues for the next one. But please do join me for the next session. Not yet scheduled. I will think about having as I mentioned, a more structured morning versus afternoon, a recurring schedule with some other live sessions TBD in between. But thanks for joining. I think this was a particularly good set of questions today, and hopefully you enjoyed, or at least appreciated, the answers. I know not all of it is necessarily material that can be enjoyed. That's probably not the right word. But in any case, thanks for joining, and see you next time.